This lecture is on continuity and limits, and we're going to do this before we actually talk about what the derivative is. The idea is that continuity is a pretty common notion. So what does it mean to be continuous? So when I think of continuity, I think of something like this. So you can draw something, or something is progressing in a continuous manner, in a manner where there are no sort of stops. So this is a graph of a continuous function, whereas this is not continuous. So if you, that's a closed circle there, if you have a graph where you have a jump, or a graph where you cannot draw it in a continuous manner, which means basically without lifting your pen or pencil, then it's not continuous. So here, notice I can draw this simply by never lifting my pen, whereas here I have to jump up here. That's why we actually call this a jump discontinuity, and then begin again. So this is a graph of a, what we'd say, a discontinuous function, whereas this is a graph of a continuous function. Now, the only reason that this is discontinuous is you have a jump here. So if you look at a different part of the graph, so if you focus on this red part here, you could say the red part is continuous. Whereas if you look at the whole graph, the whole black, drawn in black here, it's discontinuous. All right, so let's take a look at these, a couple examples from the point of view of a graph. So there are 4 graphs here. We want to say which ones are continuous. So we have A, B, C, and D. And so take a look here and look at A, and notice I can draw A without lifting this highlighter. So I would say A is continuous. Whereas in graph B, of course, I can draw from here to here, but then I have to jump, go up here, jump, go up here, jump, go up here. So B is discontinuous. And then C, notice I can draw it even though it changes what the graph is. I can still draw it in a continuous manner. So B is also continuous. And of course, D is not continuous, and there are several reasons for this. One reason, when you try to trace a graph all the way down here, you have to jump over the vertical asymptote to get to the other side. Then you go up, and then plus there's a hole right here, so you have to jump over the hole to get to the next side. And then keep going up, then another asymptote, and jump to go down. So D is a discontinuous graph of a function. And so find where the graph is continuous. So let's look at A, B, and C, and let's just do these separately. So for A, this graph is continuous everywhere, so I'd say it's continuous on minus infinity to infinity. Now for B, it's continuous on certain intervals, so I would say it's continuous between -2 and 1, and -1. So it's continuous, let's do a different color marker. So it's continuous between -2 and 1, and then it's continuous between -1 and 0. So maybe write union -1 and 0. Union, right, there's a jump here, then it's certainly continuous between 0 and 1, because you can draw it in a continuous manner between 0 and 1. And then also between 1 and 2. So union 1 and 2. And then if we look at part C, or the graph, letter C graph, you'll see it's continuous everywhere. So from minus infinity to infinity. And then finally D. D is continuous. Again, you can trace it. So let's use a red marker, and we can trace it. It's continuous, it's continuous, it's continuous, it's continuous all the way up until -2. So you go from minus infinity to -2, union, and then you have to jump the asymptote, and then it's continuous, it's continuous, it's continuous, it's continuous all the way up to here, so between -2 and 1. So -2 and 1, union, and then after you jump over this little this open circle, then it's certainly continuous above it, so from 1 to 2. Union, and it's continuous, then you can come down all the way, so from 2 to infinity. So that's where the graphs are continuous. Find the points of discontinuity in each graph. So for graph A, right, there are no points of discontinuity. And then for B, I would say for sure, if you look here, there's definitely a jump at x equal -1. So x equal -1 is definitely a point of discontinuity. There's also a jump from here to here at x equals 0, so also x equals 0. And there's an obvious jump at x equal 1 from here to here. So I'd say these are for sure all points of discontinuity. Now, depending on how you want to talk about this function, I would say x equal 2 is a point of discontinuity, but if you did include it, I wouldn't count off. Because you could argue that it's continuous from the left, but it's not continuous from the right. So depending on sort of what you want to take for your notion of continuity, you could argue either way. So it's fine to include it, it's fine not to include it. The same thing for -2 and all the points to the left of -2 or all the points to the right of 2. But the point of this problem really is to notice that definitely here at x equal -1, definitely here at x equals 0, and definitely here at x equal 1. These are all points of discontinuity. And then for C, there's none. So let's just write none this time. So no points of discontinuity. And then for D, there's a couple. So for D, obviously at -2, x equal to -2. That's actually a vertical asymptote, so that's a point of discontinuity. And then there's this open circle here, which I've sort of colored in, but that's an open circle. And so at x equal 1, and then also x equal 2, because again you have this asymptote. So the most sort of common ways to have discontinuities is to sort of jump, which we call usually a jump discontinuity, or you could have an asymptote. So you could have a graph basically approaching a vertical asymptote on that side, and then maybe coming up, going up from the top and coming down on the other. So those are two very common ways to create discontinuities. Let's talk about formulas in continuity. So basically for a formula, it's a lot like the domain. The places where you have discontinuities are where it's basically not defined when I give you a nice formula like these. So we want to find where each formula is continuous. So let's work with this f of x here. And so here I have x divided by the quantity x squared minus 4. So this is not going to be continuous where the bottom is a 0, because it's actually the same idea. So if you think about it, right, for continuous things, there's basically, two ways like I talked about before. You have a jump discontinuity. The most common way to get a jump discontinuity is to have a piecewise defined function. So that's what you're going to find. We'll do an example here in a minute. And the second way to get a discontinuity is to have an asymptote. So that would be when you have f of x equal to something over something. And so in this case, you have x over x squared minus 4, so you have to worry about the denominator not being 0. So really, it's the same as the domain. You have to worry about these three things. 1, you can't divide by 0. 2, make sure if you have a square root, it's bigger than or equal to 0 on the inside. And then 3, for the ln function, it has to be greater than 0 on the inside. So when I give you a basic formula like this, that's what I'm basically going to look for. So let's start out down here, f of x equal to x over x squared minus 4. And in part A, I want to find where each one of these is continuous. So I need to watch out for when x squared minus 4 is equal to 0. And so what I can do is, instead of moving over the 4, I'm going to factor. So this is x minus 2 times x plus 2. This is the difference of two squares. And so that's equal to 0. So I know either x minus 2 is equal to 0, so either x is equal to 2, or x plus 2 is 0, so x is equal to -2. And so I'm going to say that this is continuous. And so it's continuous on minus infinity to negative 2, union negative 2 to 2, union 2 to infinity. So I'm basically taking out the 2 points where the denominator is equal to 0, and if you think about it, that's where you're going to get asymptotes, vertical asymptotes, because the way you get vertical asymptotes is that this function basically blows up or blows down to positive or negative infinity, and the way you get that is you make the denominator basically 0. And so that's how I know that it's continuous on this interval. For the next one, let's do this. Let's do part B below it, and then we'll do the next function. So part B, find the points of discontinuity for each formula. So then it's discontinuous. I've already done all the work at x equal negative 2, and I can just put a comma and 2. Let's do g of x. So g of x is equal to x squared divided by, I don't need to go back up here, 2 minus cosine x. And so on this one, on part A, I want to find where this function is continuous, where this formula is continuous. And so all I need to worry about is when this denominator is equal to 0, because there are no roots and there's no ln. So I want to figure out when is 2 minus cosine of x equal to 0. And so that's when, if you add cosine of x to both sides, when 2 is equal to cosine of x. And my brain sort of goes ding, 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 because I know that the cosine of x is always between negative 1 and positive 1, because it looks like this. All right, this should be the same height down here. As, so it goes between 1 and height negative 1. And so cosine of x is never 2. What that means is this is never equal to 0. So this is continuous everywhere. Since the denominator is never equal to 0, it's going to be continuous on minus infinity to infinity. And then for part B, the points of discontinuity, there are no points of discontinuity for this one. All right, so this is a function that is continuous everywhere, whereas this f of x is continuous almost everywhere except for these 2 points, x equal 2 and x equal negative 2. So it's just continuous on these 3 intervals. All right, let's talk. So I want to do one more. I want to do a piecewise defined function. So oftentimes you get these jump discontinuities, and the way you get a jump discontinuity is you have a piecewise defined function. So here in this example, it says, let's find k so the function is continuous everywhere. And so the idea is that these functions need to match up when x equals 2, basically. You can graph this. So you want to think about what's really going on here. The issue occurs at 2, where you change graphs, basically, where you change formulas. And so when x is bigger than or equal to 2, you're going to use 5x squared. So if you plug in 2, then 2 squared is 4, and you're going to get out 20. So basically, up here, this is going to look like that, because it's 5x squared, so it basically comes all the way down and goes over there, but you only care about the part bigger than or equal to 2. And then behind it, when x is less than 2, you're going to have a line, which is k times x. And you need to figure out k so that it basically matches up right here. When you plug in 2, you get out 20. So the idea is if you have k times 2, you want this to equal the height of 20. And so k is going to equal 10. So if k is equal to 10x, then basically what's going to happen when it's less than 2, it's going to match up with that point perfectly. And so then you'll have a continuous function. All right, so my answer for this would be f of x. I mean, I found k, so that's my answer. But if I rewrite this, it'd be 10x when x is less than 2, and I'd use 5x squared when x is greater than or equal to 2. And the 10x comes from the fact that if you plug in 2 down here, you get out 20. So the idea is you want these graphs to match up when you plug in 2. So if I plug in 2, I need to get out 20 also. So the graphs basically match up. You know, the blue graph has an open circle here because it's only true when less than 2, but the part down here, which we can color code it, right? The red graph is given by this 5x squared when x is greater than or equal to 2. They need to line up, and then it'll be continuous there at that point. So let's talk about the actual definition of continuity. Intuitively, everyone understands what it means to be, you know, continuous. This is what we mean to be continuous. You can hear, we talk about talking continuously or hearing a stream of music, of continuous music. There's sort of no breaks in some sense. But the actual definition involves what's called the limit. So let me write down the definition. So let's say we say a function, and I should probably name it. Let's name it. We say a function f of x is continuous at x equal a if the limit as x approaches a of the function f of x is equal to f of a. So our goal for the next basically week is to try to understand in some sense what do we mean by this idea, this notion of a limit. So on the left hand side you have what's called the limit, and let me write it out. So we say that this is the limit as x goes to a of f of x. So we say this is the limit as x goes to a of f of x. And then, of course, on the right-hand side, then you could say is equal to f of a. Is equal to f of a. So I think it's worthwhile to kind of understand how all these pieces sort of match up. You know, so obviously the word limit, right, is right here, the limit. And then as x goes to a is what's meant by that x arrow to a. And of course I have f of x. So here's the f of x. And then sort of equal to is equal to, so is equal to, and then of course this is f of a. That's f of a. When you start saying this, you're going to realize when you say the limit as x goes to a of f of x, there's a whole nother area called functional analysis that has to do with basically operators on functions, almost functions on functions in some sense. And the language actually tells you that. When we talk about a function, we say f of, g of, ln of. Those are all we say e to the, but you know, this sort of is built into the language. So you have the limit as x goes to a of f of x. So limit is actually what we call an operator, and it operates on the function. But we'll get into all sort of what a limit is. Let's look at a simple example of this. Oh, and I want you guys to understand, you already know what a limit is, right? So if I ask the question, you know, what is a limit? We use this word in our language, so you can fill in the blanks below, and it says, you know, there is a blank to the amount of work I can do in a week. There is a blank to how hot a fire can get. There is no blank to what I can do if I put my mind to it. And of course, when you fill in these blanks, they're all the same thing. There is a limit to the amount of work I can do in a week. There is a limit to how hot a fire can get. There is no limit to what I can do if I put my mind to it. And it reflects this idea, the limit as x goes to a of f of x. You know, the idea that there's a limit to the amount of work I can do in a week, the idea as the week goes by, there is a limit to how much work I can do. Maybe I can't do more than 70 or 80 hours of work in a week. There's a limit to how hot a fire can get. The idea is I stoke the fire more and more and make it hotter and hotter, but it's not going to pass a certain point, and that certain point we call the limit. Same thing down here. There is no limit to what I can do if I put my mind to it. The more that I focused, the more that I work, this says there's basically no bound to what I can do, that basically I can go off to infinity is sort of the idea. And that's what this is saying, right here. This is saying what happens when I see this. I say, what happens to this function as the number x, as x gets closer and closer to a? What is going on with the function here? And so let's look at an example involving a graph, because once you kind of see this, it makes sense. And the limit's very subtle, and again, it's going to take us about a week to kind of get this down. But let's look here at the first sort of limit. This says the limit as x goes to 3 of f of x. So here's my function, and as x goes to 3, well, x are my inputs here, and here's 3. And what you want to do is, what happens to the graph? What happens to the height of this graph as you go to 3? Well, as you go to 3, it looks like the height right here is approaching 2. And so I would say, okay, my answer is equal to 2. Now, there are two different types of limits other than the one right here. There are left-hand limits. And then if there's left-hand limits, there's also right-hand limits. And so right-hand limits, left-hand limits, let me move this down. Oops. All right, so left-hand limits, the idea is it comes in from the left-hand side. Whereas for right-hand limits, well, that's not working. All right, well, we'll just ignore it. So left-hand limits come in from the left-hand side. Right-hand limits come in from the right-hand side. So as an example, we have this as a left-hand limit. So let me write it up here. The limit as x goes to 1 from the left of f of x equals what? And the idea is that, just like before when we looked at 3, there are actually two ways to approach 3. You can approach 3 from the left or the right. And so over here, if we look at 1, there's two ways to approach 1. We can approach from the left, or we can approach from the right. When you have a negative sign up here, it means approaching from the left. And so you look on to the function and you say, okay, well, what happens as you approach x from, as you approach 1 from the left? Well, the height of the function goes right here to the height of 2. So this answer would be 2. Whereas if you look from the right, so the limit as x goes to 1 from the right of f of x, so plus means from the right, you go up to the height of 3. So this answer is 3. Even though there's a hole there, the heights from the right are approaching the numerical value, the number 3. And so the limit from the left is 2. The limit from the right is equal to 3. What that means is if you look at the limit as you go to 1, because these are two different values, we say that this limit does not exist. So we usually write D and E for this. But what that means is does not exist. Let me erase that. So the idea of a limit, when I think of a limit, it's sort of like your best guess for the value of the function at that point. And when you get two guesses that don't agree, from the left you get 2 and from the right you get 3, then you don't really have a best guess because your two best guesses don't agree, so we say it does not exist. Whereas when you looked at the limit as it went to 3, from the left it went to height 2, from the right it went to height 2, so really it's equal to 2 because both your best guesses are the same. Let's look at this one, the limit as x goes to 5, and let's erase some of this stuff on the picture so I can use it. So as x goes to 5 of f of x, so here's x equal 5, and you see the issue. There's a hole, and then it's closed in down here. But if you come in from the left-hand side of 5, the limit is equal to 4. And if you come in from the right-hand side of 5, the height is still equal to 4. So those two limits agree, so we say that the limit as x goes to 5 is equal to 4. So this is sort of what you might say the limit theorem, and the idea is if the limit as x goes to a from the left of f of x is equal to, let's say, L, and the limit as x goes to a from the right of f of x is equal to L, right? Then we can conclude that the limit as x goes to a of f of x is equal to L. So this is what I'm looking for in this graph in order to figure out the limit. I'm basically looking for the left and the right, and if those two limits agree, then I know that's the limit. If the two limits do not agree, then I know there is no limit there, that the limit does not exist. Right? It's a very subtle concept, and this part E shows you why it's so subtle, because the limit as you go to 5 of the function is equal to 4, whereas the actual value of the function, right, f of 5, is not equal to 4. It's actually equal to height 1, because that's where that closed circle is. So even though the actual height is 1, the limit is 4, because as you look at the left and the right, that's where it approaches. Sometimes we say this, that the limit doesn't care what happens at the actual point. It just cares what happens around that point. Let's look at one more example and try to understand this definition of continuity using sort of what we've just learned about limit. So remember that a function is continuous at x equal a if we have the limit as x goes to a of f of x equal to the actual height. So I always think of this as, you know, my best guess is equal to the actual value. That's what it really means to be continuous from this statement. But this is the definition of being continuous at a point. Now I know that this function is not continuous at 1 and 5. It's this problem we just did before. And I know it's not continuous there because I have a jump here, and here I have a hole. And down here I'm not filling in the hole, but I have it defined down here, and this is supposed to be at height 1, although it's not. This is supposed to be at height 1. And so why is this not continuous? So why not continuous at x equal 1? And using the definition, so, you know, I know there's a jump there, I can see it, but why does it follow from this definition? So in the other part, we said that the limit as x goes to 1 of f of x was equal to, well, when you came in from the left you had height 2, and when you came in from the right you had height 3, so this limit does not exist. So it certainly cannot be equal to the actual value. Now the actual value when you plug in 1 is height 2. So it certainly cannot equal 2, which is equal to the actual value when you plug in 1. So this definition is not satisfied, and that's why it's not continuous there, really. How about at 5? So why not continuous at x equal 5? Again, you can look at this, the definition. So you want to look at the limit as x goes to 5 of my function f of x. What's that equal to? Now in the last problem we saw from the left it goes to 4 and from the right it goes to 4. So the limit as you go to 5 is the height 4. But this is certainly not equal to the actual height, and the actual height was 1, which is equal to that f of 5. Right, so it does not satisfy this definition. That's really why it's not continuous there. So and see the parts, you know, it's really important that you see, okay, here's that limit part, here's that limit part, and here's that actual height, f of a, here's that f of a. Here's that limit part, right? Here's that limit part, and here's that f of a. Here's that f of a. You know, a just changes that. Here's a is 1, here a is 5. And we can actually even go a little bit further. So let's add a piece to this problem. Why is it continuous at, and let's pick a point that we did before. I think we picked, what, 3? We did 3 last time. So why is it continuous at x equal 3? Right, by using the definition, we found last time that the limit as x goes to 3 of f of x. And so what I do is I look here, here's x equals 3. From the left it approaches height 2, and from the right it approaches height 2. And so the limit is equal to 2, and that is equal to f of 3. Because if you plug in 3, you do get out 2. And that's what makes this function continuous at x equal 3 by using the definition. Right? Here's the limit part. Right? There's the limit part. And on the other side, you have the actual height, which is equal to now. Over here, it was not equal to. It was not equal to. Right? But it's continuous. The reason why it is continuous because its limit, its best guess in some sense, is equal to its actual value. Again, limits are I think, a very subtle concept, and it's going to take a great deal of time for us to understand them. Really, limits are sort of the engine of calculus. Now, you can do calculus without understanding limits, just like you can kind of drive a car without understanding how the engine actually operates. But it sort of helps you understand what's really going on if you can kind of get your mind wrapped around a little bit in the beginning. Not completely, but just a little bit about what a limit really is. So next time, we're going to talk a little bit more about notation. I'll review notation probably. And we'll start talking about formulas. How do you find limits of formulas? And eventually, we'll reach the actual definition of what a limit really is.